How long can an information cascade last? Well, it can last forever. Once you got an odd and an even numbered user showing the same action, say 1, 1, this will initiate a cascade of ones. But you can also stop and cascade with a little bit release of private information. For example, suppose at some point this person says that instead of just writing down the public action, which will be 1 no matter what, I will also shout out my private signal, which turns out to be, say, 0. And then the next person coming in, suppose she also receives a private signal of 0. Then on the one hand, she knows there is definitely a private signal of 0 and a 0. On the other hand, there could have been just a private signal of 1 and 0 back where the cascade started, and this user just flip a coin and write down 1. Or it could have been a private signal sequence of 1, 1. Okay. Either way, it could have started this cascade. So this user may decide to actually go with 0 and write down a public action of 0, and that would break the entire chain of information cascade. And this is what we call the Emperor's New Clothes effect. A little boys shouting out there's no clothes can initiate a reversal of the cascade, because even though people know there might be a lot of people doing the same thing, they could have been following just a small tiny turning point of private signals many steps before the current time. And this explains quite a bit of social phenomena when cascades stop, ranging from certain trends in the fashion industry to totalitarian regimes collapsing. There are quite a few other variations. Okay, one is the piece not being the same. Different user would have a different PI, the probability of knowing the correct number through the private signal. And suppose you as a designer of the experiment knows all these P's, then in order to start a cascade earlier, to get an early onset of cascade, you would put those P's, larger P's users, earlier in the crowd. You make this one the one with the largest P. And this would trigger an earlier onset of cascade through these rational Bayesian agents thinking. However, if you would like to have a checkpoint later in the crowd to possibly stop a wrong cascade, then you'll put the large P's people down there. There can also be multiple levels of numbers. We have been looking at a binary number guessing game. So whichever is more likely than the other will be written down as the public action, as the guess. But sometimes, for example, on a street corner, if one person decides to tilt the head towards the sky because of a nosebleed, probably other people just continue to pass by. But suppose there are 10 people all tilting their heads looking at the sky, then the next passers-by will say, well, there might be something wrong in the sky, wrong enough that I can see 10 public action, and that will trigger me to stop walking and also tilt my head to the sky. And once that starts, then other people will follow suit, and the crowd will get bigger and bigger until the new Emperor's effect kicks in. Somebody says, hey, the first guy just had a nosebleed, that's why she tilted to look at the sky, and the crowd may disperse exactly at that point. So depending on your curiosity level and how much you need to do, keep walking, different person would have a different threshold of crowd needed in order for her to stop walking and join the crowd as well. There are many implications to this study of dependence of information or of action on other people's action. And this partially explains social phenomena such as a crowd making a decision ignoring each individual's private information. It partially explains chain reactions that are fragile and easy to revert. For example, one implication is why U.S. presidential election in the primary season had what's called the Super Tuesday, precisely to hold many states' primary election in each party so that there is no sequential, to avoid sequential decisioning. Now we have looked at this social influence model, information cascade, through a simple rational Bayesian agent thinking along basically a linear topology. And in the rest of this lecture and the next lecture, we look at quite a few different extensions. But before then, let's walk through one more extended numerical example, especially to look at the probability of correct versus wrong cascade. Suppose the underlying number is 1. Okay, this is therefore different from the previous derivation where we assume that the underlying number could be either 0 or 1. Now we say it is fixed at 1, and therefore an up cascade of 1s is a correct cascade, and a down cascade of 0s is an incorrect cascade. And we can write down the possible evolution through a tree. Okay, the first user look at the private signal. It could be 0 or 1. It branches out different paths on the along the tree, and then the second user could get 0 or 1, 0 and 1. If it actually get a private signal of 0 first and then 1, then you flip a coin. That's what F denotes, to decide with 50% chance you write down 1, 50% chance you write down 0. And then you get this possible outcome just out of the first two users of the two public actions, y1, y2, being 0, 1 or 0, 0. And you can follow through the other branches of this tree in the same way. Okay. So now we can quickly write down the following. Just looking at the first two people, we know that the probability of no cascade, just like what we discussed before, is that if x1 is 0, x2 is 1, and you flip a coin to maintain 1. Or if x1 is 1, x2 is 0, and you flip a coin to maintain 0. This would be the probability 1 minus p times half. This is p times 1 minus p times half. And you add up the two together, you get p times 1 minus p, same as before. Now the probability of an up cascade, however, is different because we now explicitly assume that the correct number is fixed at 1. So the up cascade is probability that x1 is 1, x2 is 1, or x1 is 1, x2 is 0, but you flip a coin and decide to write down 1. The probabilities are respectively p times p plus p times 1 minus p times half, and that equals to p times 1 plus p over half. And the probability of a down cascade after two user, you can write down similar expression. It is 1 minus p squared plus 1 minus p times p over 2. That equals 1 minus p times 1, 2 minus p over 2. So that's the expressions for these three possible events. P times 1 minus p for no cascade, p times 1 plus p over 2 for up cascade, and p 1 minus p times 2 minus p over 2 for a down cascade. Now this is also the probability of a correct cascade. The underlying number is assumed to be fixed at 1, and this is an incorrect cascade. Now this is just for the first two users. We can now write down the expression for a general 2n users. After an even number of users, what would happen? The derivation is slightly involved, but you can either do that as a homework exercise or look at the textbook derivation. It basically follows the same principle as before. We'll see that, first of all, no cascade, that probability is simply p times 1 minus p, the whole thing, n times. Now up or correct as cascade turns out to be p times p plus 1 times 1 minus p squared n times over 2 times 1 minus p plus p squared. And the probability of down and incorrect cascade turns out to be 1 minus p times 2 minus p times 1 minus p squared n times over 2 times 1 minus p plus p squared. This is just basically a denominator that we use to add up the terms. This factor of n is really a factor expressing the probability of no cascade. Okay. But the other part of the numerators are different because we already assumed the underlying number is 1. Therefore, that breaks the symmetry, and therefore up and down probabilities are not the same anymore after 1 or n pairs of users. And we can plot this on a graph for actually 4 different cases. Okay, 1 pair, so 2 user, 2 pair, 4 user, 5 pair, 10 user, 100 pairs, that's 200 users. Now, in fact, you can only see visually 3 lines for 1, 2, 5 pairs, because beyond 5 pairs pretty much stays as the same. Visually, you cannot use naked eye to tell the difference anymore. And I'm plotting here the probability of the correct cascade as a function of p, the common probability of getting the correct private signal across all the users, ranging from half to 1, has to be bigger than half. Okay, and 1 is the largest it can get. Now, of course, when it is exactly 1, the correct cascade is always 100% probability. But as you can see, it starts out actually much less than that, as p moves very close to half-half. With half of a chance, you're actually going to get the correct underlying number, half of the chance you'll get the incorrect one. So it's not a surprise that the probability of correct cascade increases as a function of each individual getting the correct private signal. Now, we also observe that as n increases, the chance of no cascade actually drops dramatically. And also, the probability of correct cascade is still quite small, even when n is large. And this is the key observation we want to highlight in this graph, is that the probability of correct cascade is still small even when n is large. You think that bigger n should be able to give you wisdom of crowd, and therefore the probability of getting a correct cascade should increase with n. But that does not happen, precisely because wisdom of crowd depends on the independence of users' opinion, whereas in information cascade it's exactly the opposite, with a dependence, in fact complete dependence of previous users' actions, and that destroys this independent assumption.